Hello everybody. Today we are going to be talking about section 6.3, and the title of that is Area and the Definite Integral. And basically we're going to be addressing the question of area. So we know for a lot of different shapes, we know what their areas are going to be, right? We know that the area of a triangle is going to be the length of the base times the height, and then we divide by 2. We know areas for other regular shapes like a rectangle, and that one is just base times height. We know the area for a trapezoid. So here we have a large base, a little base, and I have the height of that, and the area of this is going to be little base plus large base times height all over 2. And there are of course other regular shapes for which we know the area of. And the question that we are trying to answer is, what if we want the area of an irregular region? And of course the answer for that is going to depend on the region, right? But let me just give you some examples of irregular shapes. We could be talking about something that is not a regular shape, so it's not a square, not a rectangle, not a parallelogram. We could have maybe some kind of pentagonal shape like this. We could have, of course, we could also have a circle. For that one we happen to know the formula, but if the shape is oval or some other type of curved shape, we have this. Or more general, we can have what we're going to talk about in this class, a region that is defined by the graph of some function, right? The question is, how do we calculate all of these areas here? And the answer is, of course, we are going to break up the region into pieces, or into regular pieces, whose area we can calculate. And add all of those areas up. To get the total area of my shape, of my irregular shape. So for this first shape right here, what I can do is draw a line this way and then I'm going to add the area of these two triangles. For the pentagon, I'll do the similar thing. I'll draw a line here and here, then I get three triangles whose area I know how to calculate. For a circle, it's a little bit more complex, but what I can do is, from the center of the circle, draw a lot of rays outwards like this. Then for each ray, I draw the base of a triangle, just like so. And of course, when I add the areas of all these triangles, I'm going to be missing some area out here. But the more triangles I draw, the closer my approximation for the area of this shape is going to get. And we will, at least for the topic of calculus, what we do with something that is a region that is defined by some function and then the axes here, or as we'll see later on next week, by two functions and the region that is between them, we do the following thing. So let me draw it a little bit larger here. Let's say that this is some function f of x, and I'm looking at the region between its graph and the x-axis from some x equals a to x equals b. So imagine that this is the x-axis here. What I want to do is I want to break this region. First, I want to break the interval on which I'm graphing this. So from a to b, I'm breaking it into several pieces. Then what I'm going to do is I'm going to split this into rectangles, just like so. And then what I can do is I can add the area of those rectangles together, and I get an approximation. Of course, it's not going to be exact for the area of my function, and this is an approximation because over here, notice I am leaving out this area here, so that's some error that I get. Then I'm gaining too much area with the second rectangle here. Then I'm leaving out some area over here, and I'm gaining more area in this part over here. Or I'm leaving out, not gaining, but leaving out area over there. So just like I said for the circle, one thing I could do is I could try to break this region up into more rectangles to hopefully get a better approximation. So instead of breaking it into 4 rectangles like that, I'm going to break it now into 8. Just like so. And now let's go ahead and draw those rectangles. And I want you guys to notice, so before, I'm going to highlight what the previous rectangles were. They were here, right? So we had 4 rectangles. Now I have each of those rectangles is broken into half. Before, this guy looked like this. So before I was looking at this rectangle. Now I'm repairing the error. I get less error because instead of omitting what was here in this entire upper half, I'm omitting less area, so I'm including this piece into my calculation. The same for the second rectangle. I was overestimating by a lot the area of that rectangle because my the area of the actual shape, and here instead of overestimating by that much, my error is fixed by this amount, so I'm only overestimating by a little bit here. and so on. So the key thing to note here is that it looks like the approximation gets better when we use smaller. So when we use more and therefore smaller rectangles. Okay, so the less rectangles we use, the bigger they're going to be, and the bigger the area is going to be. The more rectangles we use, the less error we are going to get. So the closer we are going to be to the actual answer. So let's go ahead and do an example on how to estimate the area of such a shape by using rectangles. Let me go ahead and write that over here. Let's use two rectangles to evaluate, or to approximate rather, the area of the region below the graph of f of x is, I'm going to use negative x squared plus 5, and the x-axis between x equals 0 and x equal 2. Okay, so let me go ahead and draw the region that I'm talking about. I'm going to draw it on the other side of the page. So I have a parabola opening down that's shifted up 5 units, right? I have f of x equals x to the fifth, negative x squared plus 5. And what that's going to look like is, it's a parabola that's shifted up at 5 that opens downward. And I'm only interested in this between 1 and 2, between x equals 1 and x equals 2. So the area that I'm trying to estimate is that area. Okay, it's an irregular shape because I have this curved side over here, so I can't quite use a trapezoid to compute it or anything like that. So we're going to use the method that we talked about, which is where we break the region up into rectangles. And I want to do this in several ways, and you'll see in a second what I'm talking about. For part A, I want to use right endpoints for each rectangle. For part B, I want to use left endpoints. And for part C, I'm going to use it, I'm going to use midpoints. Okay. So let's go ahead and look at this. And I think I already said before, I said use 2 rectangles. Actually, I'm going to change that. I'm going to use 4. So I'm going to go ahead and use 4 rectangles for this. So let's go ahead and set up the problem. Here I have part A, so I'm going to use I'm going to use right endpoints. And let me draw the picture of that, what that's going to look like. So here I have my curve. Here is 0, 1, and 2. And now I go ahead and draw my rectangles. I want to use 4 rectangles. So I have the following picture. And now what I do is I look at each rectangle. Notice that the sides of the rectangle are going to determine an interval on the x-axis. When I say using right endpoints, I'm going to choose the point on the right. And that is going to determine the height of my rectangle. So I'm going to be using this, and this is at 0.5. In the second rectangle, I choose the right endpoint. I go up to the function that's going to determine the height of my rectangle. On this third rectangle, I choose the right endpoint. I go up to the function on the right side that determines the height of the rectangle. And on the fourth rectangle, I do the same thing. So this is the approximation versus the actual area. So we lose a little bit of area each time for this particular function. Now let's go ahead and compute it. So the actual area, I'm going to approximate it. I'm going to write this R for using right endpoints, number 4 for 4 rectangles to approximate this. And what this is going to be equal to is the area of the first rectangle. So here is A1, A2, A3, and A4. Alright, so it's area of the first rectangle plus area of the second rectangle plus the area of the of the fourth rectangle. So we have that. And now we just have to see what these are. So what is the area of the first rectangle? Is the base times height, and the base here is, well, that distance is 0.5, and I'm going to call that distance the change in x, delta x, and then the height is going to be f of 0.5. So it's f of 0.5 times delta x. Then the second area, it's, now I have f of 1, that's the height of the rectangle, times the base, happens to be the same for all of them because I'm breaking it up into rectangles of equal width. Then I have f of 1.5 times delta x. Then I have f of 2 times delta x. Okay, and notice delta x is the same for each, right? I said this, they have the same width, which is 0.5. So I can bring that delta x in front, and so I have delta x times f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. And now I just have to plug these numbers into my function which is the x squared, negative x squared plus 5, and compute this. Right? So R4, the approximation using right endpoints and 4 rectangles, is going to be delta x is 0.5, then I multiply everything by negative 0.5 squared plus 5, that's the first one, plus negative 0.5, I'm sorry, negative 1 now, squared plus 5, plus, then I have negative 1.5 squared plus 5, and then lastly I have negative 2 squared plus 5. I go to my calculator, and the easiest thing, the way I like to do this is I enter my function here, so I go to y equals, I enter my function, I exit this, then first I add all of these up, right? I go to vars, y vars, y of 1, y sub 1, which is where the function was entered. I compute this at 0.5. I get 4.75. Then, to that answer, I'm going to add, again, go to function, y1 of 1. Then, to that answer, which is the sum of the first two, I add y1 of 1.5, right? So I'm adding the third term now. Then, finally, I add y1 of 2. So this entire parenthesis should be 12.5. So this should now be equal to 0.5 times 12.5. So when I multiply this by the delta x, I get 6.25 for the answer. So that's how you would do it on the calculator, right? You want to enter your function in y equals, then evaluate at all these points. Then at the end you multiply by the delta x once you add all those things up. And that makes it quicker than plugging in this numerical version in. So that was the right endpoint use. Let me show you what it's going to be different when you use left endpoints. So again, here's the function. I'm going to make this a little bit wider so you can all see what is happening. If this is 1, 2, and this was 0, because I'm doing it between 0 and 2, I'm going to break this up into 4 subintervals like that. And now I look at each subinterval. Okay, this is 0.5 and this is 1.5. That's the x value. For each subinterval, I'm going to now choose the left endpoint. So for the first one, I choose the left. I go up to the function that determines the height of my rectangle. For the second rectangle, I look at the left side, go up to the function that determines the height. For the third one, I look on the left side, I go here, up to the function that determines the height. And finally, for the fourth one, I do the same thing. And so notice, now, when I add the area of all these rectangles, I get this with the extra stuff on top. Okay, so I'm gaining some extra area, whereas before I was losing some area using the right endpoint. So now if I want to do the approximation, the actual area is approximately R4, I'm sorry, not L4, this time I'm going to write L4, L for left, 4, because I'm using 4 rectangles. So that's, of course, the area of the first rectangle plus the second plus the third and the fourth. And you wouldn't have to write this each time. I'm just doing this because I'm teaching now. And L4 then is going to be equal, okay, what's the area of the first rectangle? Well, I still have the same base for each, so delta x is the same, it's 0.5. And then the height here now would be f of 0, whereas before it was f of 0.5. So I'm using a different height for the rectangle times delta x plus second rectangle. The height is f of 0.5 now times delta x plus the third area 3 is f of 1 times delta x plus f of 1.5 times delta x. Okay, so I can factor out the delta x from everything, and I'm gonna be left with f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. And now I go to my calculator to find what this sum is. I already have my function into y equals from the previous part of the problem, right? It's that one. Then I do vars, y vars, function 1. First I evaluate it at 0, so I do f of 0. Then, whatever I get here, I add y of 0.5. Then I add y of 1. Then I'm adding y of 1.5. So then I have a total sum of 16.5. And when I multiply this by the delta x, oops, I get 8.25. Okay, so that's how we do these things. And notice the numbers are different. Here, the right endpoints, of course, we have smaller area because we're losing some, is less than the left endpoint. And that is not true in general. So it depends on the function which one of these is larger. It's not always true that the right sum or the right approximation is smaller than the left approximation. And now the only other approximation we have left to do is part C, which has it's just asking us to use midpoint. And this is honestly the most annoying one. So let me draw out the function like this. I do my 4 subintervals and 0, 1, this is 2. For each of these, instead of choosing the left or the right endpoint, I'm going to choose the midpoint. I go up to the function that's going to determine the height. So it's a little bit hard to see, but I'll show you in the other rectangles what happens. So here the x-coordinate is 0.25. Then the midpoint here is going to be 0.75. Then the midpoint here is 1.25. And then the last one is 1.75. And notice the advantage of using the midpoint rule. You can see when we look at this fourth rectangle, I'm losing some area here, but I'm gaining some area there, right? So the error is going to be, in general, smaller when I add all of this up. Okay, so the same with the other rectangles. I'm losing some here, but I'm gaining it back over here. I'm losing some area here, I gain it back over there. I lose some area on top here, but I gain it here. So the error in this approximation is going to be smaller than the previous two, because here I'm just gaining extra area, here I lose extra area, but there's nothing to cancel out that error. Here there's some cancellation going on. So without further ado, let's go ahead and compute this. The area of the first rectangle, it's the height, which I'm going to use the midpoint, so 0.25 times the delta x, which of course is the same, it's still 0.5, plus f of, now I have 0.75 times the delta x, plus the third one is 1.25 times the delta x, plus lastly is f of 1.75 times the delta x. So that's what we have. So okay, it's delta x times the whole thing. I'm not going to rewrite it, right? It's just f of this plus f of, and so on. And when you go to the calculator and you do this, I did it beforehand, I get the answer 7.375 for this. And notice it lies perfectly in between these first two approximations. So in general, it is true that the midpoint approximation is going to lie between the other two. So now let me just talk about the general setup of this, how we set up these things. But I just want to have it in writing, right? Note the midpoint, or using the midpoint, offers a better approximation. So that's one thing to keep in mind. Of course, it's more annoying to work with the endpoint. As you saw, the x coordinates that I have to plug into the function are more annoying, basically. So now, let me talk about the general setup. And what we have is this, right? We have to find the area under some curve using rectangles, and I'm looking at it between x equals a and x equals b. I want to break this up into n rectangles when n is some integer, like this, and this determines a split of the entire interval from a to b into smaller subintervals. So here I'm going to say this is x0, which is equal to a. Then I have x1, x2, x3, etc. B is going to correspond to x sub n. Then before that I have x sub n minus 1, x sub n minus 2, etc. Right, these are the x coordinates. And if I am looking to approximate my area, the total area is going to be approximately, well, I can use left endpoints with n rectangles, and that is going to be, we saw the delta x is the same, and in fact the delta x has the value, the total length of the interval, so b minus a divided by the number of rectangles that I'm going to use. So it's b minus a divided by n. That is what delta x is. So I have delta x, and then for left rectangles I'm gonna do the left end points. So if I do the first rectangle, it's f of x0, then I have f of x1 all the way to the last rectangle, which uses f of x sub n minus 1. So that's the left approximation. I could also approximate it with the right endpoints, right? So that's again same width for the rectangles, and now the heights, I look at each rectangle, I choose the right endpoint for the height to calculate it. So I do f of now x1 plus f of x2 plus dot 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 f of xn, because in the last rectangle the point on the right corresponds to xn, which is just the value b. Or, as we saw, I can use the midpoint. So I can use m sub n, and that is going to be the same delta x. However, the thing that I plug into f is different. It's the thing between x0 and x1, so it's the average of the two. It's f of x0 plus x1 over 2 plus, for the next rectangle, it's the average between x1 and x2, and the last one, of course, is f of x sub n minus 1 plus x sub n all over 2. Right? Okay, you don't have to remember this formula. All you have to really think about is how I get these endpoints. So first, draw your picture, right? Just like I did in the example that I solved. Draw your picture, draw it large enough so that you can label your x-axis with all these points. And then you say, okay, if it's the right approximation, I pick the point on the right. If it's the left approximation, I pick the point on the left. If it's the midpoint, what is between these two x values? You compute that. You don't have to remember what I wrote here. I'm just writing it so that we have the general setup on paper. So, as I mentioned, the approximation, right, so one thing to note is that the approximation is going to get better so it gets closer to the actual area between, okay, the graph of some function and then the x-axis, for example, if we use more rectangles. Right, so that's one thing that is very important to realize. So that gives us one way to define the actual area. So here's a definition. So let's say that we have some function, let f be a non-negative continuous function on some interval from a to b. Then the area, let's call it A, of the region under the graph of f of x and of course above the x-axis from x equals a to x equals b. So it's exactly this picture right here where this represents the graph of f of x and this is the x axis, right? So it's exactly this picture. The actual area is going to be defined in the following way. A is equal to, I have f of x1 plus f of x2 plus etc. f of x sub n, if I'm using n rectangles, times delta x. But since this approximation gets better and better the more rectangles we use, I'm going to let little n, which is the number of rectangles that we use, I'm going to let that approach infinity. So it's the limit of this expression as little n goes to infinity. That is what the actual area is going to be. And what these x1, x2 are not necessarily right endpoints. So one thing to note is that this x1, x2 all the way up to xn are points in the subintervals. So x1 is from the first subinterval, x2 is from the second subinterval. And okay, they could be left endpoints, right endpoints, midpoints, or it could be anything else. For example, you might choose the point that's like a third of the way in each subinterval or something like that. So it could be anything inside the subintervals. That's one thing to note. Here, the delta x is always equal to b minus a over n, because we have an interval of length b minus a and I'm splitting it into n pieces. So that represents the width of each little rectangle. And this fact that we take the limit as n goes to infinity, this means we use infinitely many rectangles. So in other words, okay, we don't know how to use infinitely many rectangles. How will we do that by hand? We are using more and more rectangles, and we see what the value of our approximations approach, and that is going to be our limit. So there is a fact and it's the following: it doesn't matter what you choose in each rectangle. It turns out that if this limit exists, then the actual area is the same as limit as n approaches infinity of, you could use the right approximation, or is the same as limit as n approaches infinity of the left approximation, and is the same as limit as n approaches infinity of the midpoint approximation. So it doesn't matter which one you use, you're going to get the same answer for some functions which we call integrable, as we'll see in a second. So it's not true for every function, right? But for those functions where this limit exists, it doesn't matter which point we pick from each rectangle. We can pick the left from the first, the right from the second, midpoint from the third. This limit will still give you the same answer. So now we have a definition, because the title of the lecture says areas and a definite integral. So we talked about areas, but now I want to talk about the definite integral. So here's the definition. Let's see. So again, we have a continuous function on some interval. So let f be a continuous function on the interval from a to b. And if that limit that we talked about limit as n goes to infinity of f of x1 plus da 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 plus f of xn times delta x, if this limit exists, regardless of how we choose the xi's, so regardless of how we choose x1 all the way to xn from each rectangle, then this is called this limit is going to be called the definite integral of f a to b. So the notation for that is just like the same notation we had for indefinite integrals. So it's the sine, I have f of x dx here, not delta x, but dx, and then instead of just leaving it like that, I write a down here, b up here. So this is equal to the limit as n goes to infinity of f of x1 plus f of x2 plus dot f of xn times delta x. And here, let me write what this is. A is going to be the lower limit. So that's the name what we have, right? A is the lower limit of integration and b is called the upper limit. Of integration. So the question is, okay, I say if this limit exists, blah blah blah, then this is the definite integral. The question is, when does the limit exist? When does this limit exist? And the answer to that is if f is continuous, on the interval from a to b, then the integral, or the limit, right, from a to b of f of x dx exists. And in this case, we say that f is integrable. On the interval from a to b. Right? So that integral is going to exist for continuous functions. In other words, that limit is going to exist, right? We're going to get some number for the area, or in some cases we might get infinity, so that's also possible. So notice that on the previous page I first talked about non-negative functions, right? And I say that this limit is the area under the curve, right? The area under the graph. Over here, when I talked about the definition of the definite integral, I didn't specify that f has to be non-negative. I just said it's continuous. So what happens if f is negative? Or what happens if we have some parts where f is positive, some parts where f is below the x-axis, right? In here, I never say anything about area, so the integral here is not going to be the same as the area under the curve. So let me talk a little bit, and that'll be the end of the lecture. Let me talk about just the geometric interpretation. of the integral, and I'll draw a picture where I have some function that is not always non-negative, right? So it has some parts where it's going to be negative. So here's the x-axis, and I'm going to start with, okay, here's x equals a, here's x equals b. I'm going to start with some function that maybe does this. It's positive for some parts, then negative, then positive again. If I just did from a to this point here, then the integral would just be the area, right? Because we saw that that limit represents the area, and it would give me area 1. Here I have some other area, but that lies below the x-axis, so it's a little bit different. So area 2 is the one that we need to think about, and of course area 3 is the area that's below the graph of f. So if I did an integral from this point here up to b, I get just the value of area 3. So the key thing to note is that the integral, the entire integral from a to b of f of x dx, where the graph of this is y equals f of x, is not always the total area between the graph and the x-axis. This is only true for positive functions. So for f greater than or equal to 0. What the actual integral means, so the integral from a to b of f of x dx, what this really means is the area above the x-axis but then we subtract the area that lies below. So in other words, I take area that's above the x-axis to be positive, and I take the area that's below to be negative. So this should be equal to, at least for the picture that I drew, it's A1 minus A2 plus A3. So I take A2 to be with a minus sign because it lies below the x-axis. And I'll write it here, area below the x-axis is considered to be negative. And that's the interpretation of the integral. So let's do a quick example. let me do it for this left of this sheet of paper that I have, whatever's left of this. If I'm looking at the following function, and let's say that this is x equals 1, x equals 10, and I'm telling you that the area here is 5, the area here is 2, the area here is 1.5, 1, and then maybe a 3 here, then for what I drew here, the integral between 1 and 10 of my function is going to be some number. The integral between 1 and maybe this is x equals 3 here, then maybe that x value is x equals, let's say, 6. The integral between 1 and 6 is some other value. And then let's do one more. Integral between maybe 1 and 2. I'm sorry, 1 and 3, not 2. Is going to be something else, right? If I go, I'll do the 1 and 3 first. I'll do this lower example first. Then it's going to be the net area. So it's going to be just 5. Right, so it's the actual area because here it's positive. But if I go between 1 and 6, it's the area that's above, so 5 minus the area below, so 5 minus 2, plus I still have this part, 1.5. So it's 3 plus 1.5, it's going to be 4.5. It's not the sum of all these three, which would be 8.5. It is just 4.5. Okay, and if I do, of course, the integral from 1 to 10, what I end up with is 5 minus 2 plus 1.5 minus 1 plus 3. So when I add all this up, notice the minus 2, minus 1, and the 3, they all add up to 0. So it's 5 plus 1.5, it's 6.5. Okay, so that's the definite integral, and that is how we deal with areas under functions. And I'll see you guys on Monday, where we are going to learn the reason why we call this the definite integral. So we're going to learn the connection between integrals and area, and how we use indefinite integrals to compute all of this. I'll see you guys Monday. Have a great weekend.